Hello, ladies and gentlemen. I'm Ekaterina Guryanova from MIREA, Russian Technological University. I'm here to present my research paper, Active Strain Statistical Models for Reconstructing Multidimensional Images of Lung Tissue Lesions. Coupling augmented reality data with data from previous medical studies is most useful for surgeries on organs with little movement and deformation, e.g. skull, brain, and pancreas, as there is opportunity to more clearly define the edges of the organ. The proposed coupling methods can be used on other operations. Besides, organ imaging techniques can compensate for the lack of tactile feedback during laparoscopic surgery for providing the surgeon with visual cues, improving hand-eye coordination, including robotic surgery. Using the combined images of MRI, CT, angiography, and ultrasound individual adjustment of inclusions, and cutting planes, optimal position of pacentesis needles and position display of the organ main component are realized. Blood vessel structure data can be superposed on this surgical cavity using vessel counter recognition. For this purpose, a model for identifying vessel counters in the video stream was developed using active strain statistical models for recreating multidimensional images. The training procedure for active appearance models begins with normalizing all shapes position to compensate for differences in sail, tilt, and offset. For this purpose, the so-called generalized reconstructing analysis is used. Purpose: to investigate computer model of contour selection to propose a model for identify vessel contours. A literature survey. The mathematical apparatus of active appearance models has been actively developed at the moment to approach to the construction of such models. Can be distinguished. The classical one, initially proposed by Curtis, and verse composition-based proposed by Mattis and Baker in 2003. Math is based on constructing a model of lungs affected area, and deformable models give relatively high recognition rates on extensive collection of images with a potentially large number of lung images. The learning experimental procedures was carried out on the computer tomography images of lungs with the affected parts. On this slide, we can see the anomalies such as the COVID anomalies. Computer model of contour stream. The model process here consists of following steps: extraction from the training images of the textures that best match of basic shape. Region mapping is carried out using piecewise interpolation of the training image. From the training image for the textures that best match the basic shape. Region mapping is carried out using piecewise interpolation of training image resulting from triangulation to be corresponding regions of the texture to be formed. A matrix is formed for the textures, each column containing the pixel values of corresponding texture. Similar to the S matrix, the texture used the training word single channel, grayscale, and multi-channel RGB color space. First, consider the common parts of the true approach. Two parameters are modeled in the active appearance models: shape-related parameters, shape parameters, and parameters related to a statistical image model or texture appearance parameters. Before use, the model must be trained on a set of pre-marked images. Markup of images are done manually or in a semi-automatic mode when using an algorithm to find approximate mark location, and then they are clarified by an expert. Each mark has its number and defines a characteristic point to the model we'll have to find during adaptation to the new image. Example of a markup at this slide. In a model of this type, the authors also need to calculate the vectors of combined parameters, which is given by the following formula. There, WS is the diagonal matrix of weight values that allows balancing the contribution of pixel distances and pixel intensities. For each element of the training sample, the texture shape pair, its vector B is calculated. Then the resulting set of vectors is combined into a matrix, and its main components are found. In this case, we synthesized vectors of combined shape and texture parameters is defined by the following expression. B here VC is the matrix of principal components of the combined parameters, and C is the vector of combined appearance parameters. From here, obtain new expression for the synthesized shape and texture. Synthesized shape and synthesized texture, S and T. In practice, the matrix free is also subjected to removing noise components to reduce the effect of overfitting and reduce the number of calculations performed. After calculating the shape, appearance, and combined parameters, this so-called prediction matrix R is required, but this sense of minimum root mean per square error would satisfy the following linear equation. Experiment procedure, active strain statistical models superimposed on the texture presents on this slide. Analysis of Octaform model. The model of active deformable forms was trained and verified to identify contours. Preliminary training gave a confidence score on 0.75, the result of unsatisfactory. The training sample was expanded and number of reference points was changed to 128 per closed counter. As a result of training, confidence increased to 0.937. The implementation of contour detection was performed with the confidence at least 0.88 in contrast to the level on 0.73 for the gradient method. Conclusion. A method for constructing a model of the contours of lung segments to identify affected tissues is shown. Strain-statistical models are used to reconstruct multidimensional images to build contours. The model showed an accuracy of detecting contours equal 0.1 millimeters, which meets the requirements for detecting affected lung tissue and can be used in a medical system for early diagnosis. Acknowledgement. The project is supported by Foundation for Assistance to Small Innovative Enterprises in Science and Technology, Russian Federation. Project number 63437, application NTI 84099. Within the framework of the implementation of the innovative project, development of an intelligent software package for the preventive diagnosis of human respiratory diseases based on active deformation and statistical models for recreating multidimensional images using an immersive environment to implement HealthNet action plans, roadmaps. Thank you for attention. We can go to the question.
Thank you for the presentation. Are there any questions? I have one for you. So did you take under consideration the change of the shape of the lungs during these different breathing phases?
Please repeat the question.
If you have considered that the lung changes its shape when we inhale or exhale, it changes, it becomes larger or smaller, and if you took under consideration this effect in your model.
Yes, we research this effect by many data sets. We use the CT data of Moscow Radiology Center and with the help of experts marked them very detailedly. We researched the effect about you said in state training procedure by with experts of radiology.
Okay, thank you very much. And we can go to the next presentation.